that is related to what you just saw as a demonstration. It also relates to something that kind of is in my background. I don't do that anymore, but in the past I have done it. So because we are dealing with bitwise operations in this class, so I just want to make the connection between what the demonstration is about, and also what we are doing in this class. Do you guys have questions in the back? Okay, very good. So we have to make the connection. So bitwise operations, why do you think we need bitwise operations? We talked about that a little bit on Monday. So do you still remember why we want to deal with bitwise operations? For input-output, okay? And input-output is related to what you just saw, okay? So what I want to do is kind of bring up the web page for the robot that Danny was using. And in order to program something like this, when you want to turn on the motor, you have to turn on a pin, okay, a certain pin on the circuit board, okay, and that is connected to a certain pin of the microcontroller unit, an MCU. And that, in return, from the software perspective, is 1 bit out of a 8-bit integer. So from one perspective, you can look at the 8-bit integer as a value, as an integer value from -128 to +127. But on the other hand, you can also look at it as 8 individual bits. This bit controls this motor, this bit controls that motor, this bit turns on this LED, that bit turns on the other LED, and so on. So it makes sense that you want to be able to turn on one without affecting any of the other ones, or turn off one without affecting any of the other ones. Is that making any sense? Okay. So what I want to show you is, why do we want to learn about that type of programming? Because when people think about programming, they think about mainframe type of programming, web programming, web scripting. They think about database programming. They think about app programming on a cell phone and stuff like that. But they usually don't think about this type of programming, which I think there's a lot of opportunities in this type of programming. So instead of showing you what type of programming I'm talking about, I'm demonstrating this concept a little bit differently from the morning class. So I wanted to show you a snap-on torque wrench. Okay. And I want it is digital. There we go. So here is a $500 torque wrench. It's a snap-on, and it's a computerized torque wrench. And okay, it doesn't seem like we're not in a computer science class anymore. This sounds more like automotive technology, right?
No,
they deal with torque wrenches.
Well, I mean, if it's digital, there's got to be a component.
Exactly. Okay.
Relates.
Yep. So this one is digital, but I think from my perspective, this one is primitive. Okay. Let's take a look at the feature. Just look at the picture here. It's got a display. There's one button here. There are a few buttons here, left, right, plus, minus, and that's it. Okay. That's the quote-unquote user interface. So you can use that user interface to dial in a torque amount. And when the torque wrench, when you tighten up a lug nut, for instance, up to that torque, it will beep you and say, okay, we have reached this amount of torque. For those of you who don't know what torque is turning force. Okay, how hard are you twisting something? That's torque. And for many applications, you really want to know how much turning force you're putting onto a lug nut, for instance. If you don't put enough on, your wheel may come off when you're driving on the highway. If you tighten it too much, you can warp things. You can strip, the stud itself. Okay, and those are all, not things that those are not the kind of things that you want to happen when you maintain the car. Okay, so a torque wrench, is useful. And we want to take a look at the quick features here. So the feature is a digital torque wrench. It doesn't really describe how to use it. Okay, that's okay. I think it really is just dial in the torque amount, and then it will beep you or vibrate or something to let you know that you have reached the amount of torque. So imagine yourself in an auto shop. Okay, so in the auto shop they have air compressors running. They have these compressed air operated equipment, which can be very loud. You have cars running, engines running, and so on. So when your torque wrench is beeping, sometimes you don't notice it, or you have to really listen to it to see whether it is beeping at you or not. So I'm thinking you can turn this into, you can make a digital version of this, but with no user interface on the torque wrench itself. And go like, then how do we set anything? How does it notify me that I have reached the amount of torque? Bluetooth. A Bluetooth-enabled digital torque wrench. So you use your app, on an app on a mobile phone, you use an app, you dial in the torque, or you can make it report the torque continuously. Okay, 75, 76, 77, 78, yep. Not a whole lot. I mean, I have a Fitbit, and it's good for 5 days. One recharge is good for 5 days. And I would imagine, in a torque wrench like this, you can put in a fairly good size, lithium-ion rechargeable battery, as opposed to the tiny little one that goes in here. So it's not going to be too bad. I mean, you can definitely last a whole day, using Bluetooth on the device itself. On the tablet, it's a different story. Okay. So what type of programming are we talking about when we are talking about this type of device or application? And what type of processor are we going to use? This is going to be small, right? It's not a PC, it's not a laptop, it's not even a tablet size, because you don't really need that much processing power. It doesn't have a touch screen, so it doesn't need a whole lot of processing power. So the computer, quote-unquote computer that goes into these things are really, really small. Depending on the demand, some of these can be very tiny and very inexpensive. So the next one I want to show you, the next page I want to show you, is a particular electronic part that can be used in these applications. This is only one of the many families of microcontrollers that can do the job. So it's called an AT-Tiny, which is an entire family of controllers. So what I'll do is I'm going to limit the features so we can just focus on one particular part here, or two. Okay. So now I have narrowed down to a particular part. This is a picture of what the chip looks like, and obviously there's no scale in this picture. So what you can do in order to imagine the scale of these things, like how big these things really are, is to look at your the fingernail of your pinky. And most people can fit between 6 to 8 of these chips on their fingernail of the pinky. If you have long fingernail, it will fit more. Okay, there's a regular size. Okay, there's a regular fingernail on your pinky. It will fit about 8 of these, 6 to 8. So they're really tiny. And when you look at the cost of these things, if you order 4,500 of these things at a time, they are 40 cents each. If I give 4 dimes to you and you walk into the bookstore, what can you buy? If you walk into the cafeteria, can you buy a banana with that 40 cents? There you go. Okay, that gives you a sense of how inexpensive these things are. But you have to buy 4,500 of these things to get that price break. But 4,500 is nothing. Even though the torque wrench that we just looked at is $500 something, do you think Snap-on can sell 4,500 of those things per year? Easily, just like that, right? I mean, you have mechanics, in these auto shops just waiting for the tool truck to stop by, because to them that's their toy store. They go in, they go like, oh, this is nice, oh, that is nice, and then before they know it, they'll be spending thousands of monies on sockets, wrenches, and stuff like that. Okay, so 4,500 is not that much when you're talking about a production type of product. Okay, not a one-up type of project, but a production product. But what you're paying, for the inexpensive device, the tiny little device, and in terms of power consumption, it is almost next to nothing. Okay, it doesn't really consume much power. But what you're paying in price is the core size. It's an 8-bit core, which means when it performs arithmetic operations, it can only perform arithmetic operations on 8-bit integers. Now you can combine those instructions to work on 16-bit, 32-bit integers, but it's not a 32-bit processor. As if that is not bad enough, it has a speed of 12 megahertz. It's not in gigahertz, it is in megahertz. Okay? And when was the last time you saw a PC that runs in the range of 10 to 12 megahertz? 30 years ago. Okay? With the IBM AT computer, they ran at the stock one ran at 8 megahertz, and then the aftermarket ones can turbo boost to 12 megahertz, and that's considered like super duper fast. Yeah, they have turbo, right? There's a button on the computer that says turbo. Yeah, you turn off the turbo when you're playing games. You turn it off when you're playing games because most games were written using tight loop timing. So if you turn on the turbo when you're playing games, everything is too fast. So you turn off the turbo when you're playing games. But it's before the time of most people in this class. And when you look at the programming side, this is how much space you have to store a program. 256 by 16. It must mean 256 megabytes by 16 modules or something along that line. No, it means 256 by 16 bits. Okay? So you have a program space, and the entire program space of this device is 512 bytes, half a kilobyte. You have to write programs that fit into this space. You have 32 by 8, which means 32 bytes for your variables. That's it, okay? 32 bytes, that's all you have for your variables. So what you're paying in terms of price for an inexpensive small device is development cost. Because you cannot just write a program in C++ or worse, Java, and expect it to run here. You have to hand code in assembly programming language for these devices in order to fit as much logic in it as possible.
C can run on that?
Not this particular model. There are other AVRs where you can run C programs, but not this particular one. In order for C to run, you need about 2 kilobytes or so to run comfortably, and this one only has 32 bytes, so that's not nearly enough. But programming these things is a little bit different because the possibilities are limited only by your imagination. Okay, because the cost of the device is no longer a barrier of, oh, we can put a processor into this whatever. Toasters. Okay, why would I want to put a processor in the toaster?
You would burn your toast.
Exactly, you can better control the temperature, but from the manufacturer's perspective, I might be able to lower the cost of a toaster by making it electronic instead of electrical or electric mechanical. Because the way toasters work, is they have a bimetal strip. When it heats up, it bends, and then that's how it can tell that it has reached a certain temperature. And by changing the slider to adjust the toastiness, you are basically just changing the offset of the bimetal thing, so it will break the circuit at a different point, and that's not reliable. Okay, it's not reliable. It's not very repeatable. So for toaster 1, 2, and 3, they can all have different settings for the same toastiness. But for something that has a microcontroller and a thermistor as a sensor, you can make it very consistent and inexpensive to manufacture as well. Okay. But the cost is no longer an issue. I mean, we could have done this, let's say 20 years ago. But the cost of the computer, the processing part of it, is prohibitive. Nobody's going to buy a $1,500 toaster. Well, okay, one person may, but Bill Gates, especially if the toaster runs Windows, right? But these days, the cost of the processor is the least of your worries. The heating element is going to cost more. Okay, the connectors of the toaster is going to cost more. You have no idea how expensive connectors are. Like USB connectors, those are pretty expensive stuff on the circuit board. It is actually surprisingly expensive compared to the more sophisticated parts on the computer. Okay. But the whole point is, when you look at what type of programs can run on the desktop like this, very limited. Okay, people use it for online browsing, and even for office applications. Most people are now moving onto the web, cloud-based word processing, spreadsheet, even Photoshop is online. Okay, so you don't really write a lot of applications that run on a personal computer anymore. Mobile devices. Okay, we have a lot more possibilities with mobile devices, but even with a mobile device, well, you can only do so much. You can't really toast your bread with your mobile phone, right? You probably don't want that either, right? Just in case there's a software issue, you don't want it to kind of burn your pocket when your phone is in your pocket. But in terms of other applications, refrigerators, okay, they are already starting to be computerized. Ovens, stovetops, what other? Oh, washing machines, dryers, and so on and so forth. A lot of those appliances are already computerized. Okay, so if you know how to program these MCUs, microcontroller units, you open up a lot of possibilities. People are now talking about smart energy, okay, solar panels, wind generators, and so on and so forth. You want to save power. You want to put motion sensors in your house so that it will turn off lights when there's nobody in the room, or if no one is in the room, you can have a damper and change the air conditioning circuit so they won't send cool air or warm air into a part of your house that nobody has been there for 2 hours. Okay, that's all applications for these days. Okay, so I just want to expose you guys to this type of programming, which is called embedded system programming. I was in this industry since the 90s, and that was basically when it started to take off, because a single controller board, single board computer, was about $200-300 at the time. So we are talking about $300 in 1990. So that's probably about what, $600 now these days. Okay, as compared to 40 cents. So we are looking at an explosion of possibilities here, and I just want you guys to be aware of this type of programming, because if you are interested, go join the computer science club, because programming a robot is a fun and easy way to get into this type of programming. Yep.
Without sounding like a stalker, so while we're on the subject, I ran across your website and you had something about like a microcontroller. Is that kind of the same?
You mean the Dr. Tech website?
Yeah.
I think that's probably from my history of teaching a class over at UC Davis.
Yeah.
Are you talking about
Yes, I think it's
develops?
Yeah.
BotBrain?
Yeah, I think that was
Yeah, BotBrain is actually an older design. I actually completely redesigned this thing, but I want to show you what I use it for. It's for micro mouse design at UC Davis. I used to teach a class over there, so I want to show you a kind of like a short video to show you the one type of embedded system programming. I'm not going to turn on the sound. It's not going to be very interesting, but I do want to turn off one thing of the lights. I'm going to skip a little bit to the actual portion. Okay, so here's a robot. The size of the robot in terms of footprint is about the same as your palm, okay? It is fully autonomous. In other words, it's not pre-programmed with the configuration of the maze. It is not remotely controlled. It has to learn the configuration of the maze by using sensors. And all the time when it's doing this, it wants to figure out how to get to the center of the maze as quickly as possible. Okay? And plus all the basic stuff, even making the motor rotate one step is done by software. And that software, or that program, that code, is written by the students. So the students basically put the whole thing together. They purchase simple parts like motors, wheels, ball bearings, wires and stuff like that. But they designed their own circuit board. They wrote their entire program and they put the whole thing together.
How would it know not to read one of those openings as?
Because it knows that if it goes in that direction, it will be further away from the center. So it tries the shorter path first. If the shorter path cannot reach, if there's no shorter path to reach the center, then it will try the next shorter path. That's in general how the algorithm goes. Okay, now the question is, how big do you think is a program like that in terms of number of bytes?
It's like probably like a line, though, maybe like 200 lines.
Oh no, it's much bigger than that. Yeah, because you also have the quote unquote AI portion, so that it will do the planning and try to get to the center as quickly as possible. It needs code to read the sensors. It needs code to control the motors, and to do correction, because sometimes it's not lined up correctly. It has to detect that it has an error and then make the correction. The answer is about 32 kilobytes. Okay, so even for an application like this, the code size is only about 32 kilobytes once it is compiled. And those programs are written entirely in C and C++. There's no assembly code involved. Okay, so I just wanted to show you, what type of programming can be done, and it's I think it is fun, but more importantly to you guys, it means job opportunities. Okay, because we are already seeing the popularity of drones. Right, 5 years ago, to own a drone and to fly it around was either impossible or it's very expensive. These days, how expensive is one drone? Just one that can carry a small camera, so you can shoot pictures or videos.
$50.
Right?
$50.
$50 will get you one, but to get into if to get something more professional is about $400, and to get a production level type of drone is about $2,000. But that's basically unheard of 5 years ago. Okay, 5 years ago, if you want to fly something that can take a video and be able to remotely control it, was a lot more expensive. And these days, people can take videos. If you just go to YouTube and watch and look for videos shot by these drones, you will find amazing stuff. I think one guy flew a drone into fireworks when it's still going. No, I'm not kidding. And it was really impressive, because you would never fly an airplane or a helicopter in the middle of a fireworks display, but with a drone, he did it. And it was amazing. You can make it fly through small places, okay, like between buildings and whatnot. The possibilities are endless. But remotely controlling one is only one way to use a drone. Making it autonomous is even better. Now think about what you can do with an autonomous drone, just in terms of commercial applications. Does anyone live or work close to Davis, the fields? No one? Does anyone drive by the causeway, occasionally? So you will see the dusters, right? Airplanes, to basically drop pesticides and whatnot into the fields. That takes a person to operate it, okay? And with a person, you have to pay for insurance and all kinds of stuff like that. You can automate it. With a drone, you can automate. Now, the best part about automating it with a drone is you can do, automated, mapping, so you don't have to use, apply pesticide to the entire area. You can basically just map out which part needs how much pesticide and control the spraying, so you can, one, save the environment a little bit, and two, save the cost, right? You don't have to carry and spray as much material.
You also have to pay gas, right?
Right. Well, the drones will still need gas, but it will be less than a manned an airplane with a person. So, so there are endless possibilities with automation, and with automation, knowing how to deal with these controllers, can be helpful. And in order to get to these controllers, or know how to program these controllers, bitwise operations is also kind of like a basic thing to it. So that's why I'm gonna make that connection to what we talk about in this class. So getting back to the really, really boring stuff, are there any questions about bitwise operation? Has anyone tried out the quiz? No one. Some people might have. I saw 22 attempts, so I'm not sure, how many of those attempts came from this class as opposed to the earlier class. But I would get to it, because even if you completely flunk out the quiz, it's okay. You can take it again and again and again. And it only keeps your highest score. It's not taking your average score. So you can always start early and give it a try. Okay, it doesn't work, and then, try again. But the point is, you want to spend time on these topics because they will be in the exams. All right, so let's go back to logical versus bitwise operators, kind of one last time. And then this time we'll talk about something that is the application of bitwise operations. So I'm going to slide to here and just kind of remind ourselves, what is a bitwise operation. It is an operation that is applied to each individual bit of the expressions of each integer. And the AND operation is just that 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0. The only time you get 1 back is 1 and 1. Okay, and then the OR operation, I'm not going to repeat it. So now the question is, what do I need to do in order to make sure that bit n of an integer is a 1? What do I need to do to turn it into a 0? I don't want to affect any other bits, okay? Because with an 8-bit integer, I want the other 7 bits to remain exactly the same. I just want to make sure that one of those 8 bits is either a 1 or a 0. Okay. Yep. Well, you can give me the answer once I give you a concrete example, then we can kind of try to work this one out. Oh, no, mouse pad. I want mouse pad. There we go. Okay, so let's take a look at a particular integer here. I'm going to take a look at 165 as an 8-bit integer. I want to do the following. I want to make bit, let's see here, 165. I want to make bit 5 a 1 and bit 6 a 0. Okay, so that's what I want to do. So assuming that bit 5 is controlled to one particular motor, and then bit 6 is controlled to is connected to another device on the robot, I want to turn on one and turn the other one off, and as a result, I need to do this. So how do we use bitwise operations to do this? The first thing is you have to convert the number into a binary number, because until we see 165 as a binary number, we don't really know the values of each individual bit. So it's hard to visualize what we need to do and come up with a solution of how to do it. So we'll go ahead and convert 165 into its binary representation. Do you still remember how to change a value into a binary representation? You think in base 2, right? So it starts with what? 128. Okay, we can do it step by step. There's no need to rush and get it all done in one step. So we have 128 plus, oh man, my math sucks. Is it 37? 37, right?
Yeah, that's better.
Okay, so now we have 128 plus 32 plus 5. And I think the other one is pretty easy. 5 is 4 plus 1. Okay, so all we are doing is to break the number down so that it becomes a sum of powers of 2. And more importantly, we only want to have either 0 or 1 of those powers of 2. We don't want to say, oh, that's easy, it has 165 ones. Well, that's not going to help. Okay, so you have to start with the larger powers and then move your attention to the smaller ones. Once we have this, we can now say, oh, this is the same as 2 to the power of 7 plus 2 to the power of 5 plus 2 to the power of, what is for 2, okay, and then plus 2 to the power of 0. Is that working out so far? Okay, so I'm just looking at each power of 2 and spell it out. This is, 2 is the base, and then 7, 5, 2, and 0 are the exponents of those powers. Are we still doing okay so far? Okay, so this is just a step-by-step process. Now, once we know 128 is 2 to the power of 7, what do you think it looks like as a binary number? Remember, in binary number, it can only be zeros or ones, and then padding zeros on the right-hand side is just multiplying something by 2. It's 1 followed by how many zeros? 7 zeros, exactly. So 1, 2, 3, 4, 5, 6, 7 in base 2. So the next one is easy, right? 1 followed by 5 zeros in base 2. And then 1 followed by 2 zeros in base 2. And then plus 1 with no zeros because it has an exponent of 0. So if you have an exponent of 0, that means you don't have any zeros on the right-hand side of the 1. Are we still doing okay with this step? This is kind of like the trickiest step of all the steps. This is the one that is the trickiest because we are converting powers of 2 in base 10 into its binary form. But if you remember, you just use zeros to represent the exponent, then it's not really that difficult. But the next step is going to be pretty easy because we just need to align everything so that we can see how the digits line up. So I'm going to line it up like so. And after everything lines up, the addition is pretty easy to do because for each column there are either zeros or ones. Okay, you cannot have a carry in this case. So we have 1 0 1 0 0 1 0 1 in base 2. 165 is 1 0 1 0 0 1 0 1 in base 2. Are we still doing okay so far with the process? Okay, the process is more important than the actual details. Okay, so I want to turn bit 5 to a 1. So let's focus on one task at a time. Okay, we want to enable bit 5. Where is bit 5? This is bit 0, bit 1, bit 2, bit 3, bit 4, and this is bit 5. It's already a 1. Okay, but I don't know that. Okay, I do not know that bit 5 is already on. So I want to perform an operation that will turn on bit 5 or turn bit 5 into a 1 regardless. Whether it was a 0 or 1 before doesn't matter. Okay, this operation will always make sure that it ends up as a 1, but without affecting any of the other bits. Which operation do you think would be helpful for this? An OR, exactly. So now we have 1 0 1 0 0 1 0 1 in base 2. We want to perform a bitwise OR operation, which is the vertical bar on the keyboard, and that's shift backslash on the keyboard. Okay, so we want to figure out what to specify here. Now, I only want to change that one bit. For all of the other bits, I want to preserve their original value. That really is the tricky part. Okay, so what do I need to do to preserve the other bits?
Give it a number. The 6th bit is going to be 001 followed by 5.
Okay, let's take a look. I think you're onto it. Okay, so I want to preserve all of the other bits. So that means this one I still want to end up as a 1. That one I still want to have a 0. This is the one that I need to change. Make sure it's a 1. But the rest I want to preserve. So now the question is, what can I put here of a bitwise OR to make sure that this is a 1? And at the same time, this 1 has to be preserved as a 0.
That 0 is going to keep whatever was there.
Exactly. Okay? That's because 0 is the identity of OR. Or I should say false is the identity of OR. Okay, let's say you have an unknown bit. Let's say it's bit x. Okay, so x itself can be 0 or 1. X bitwise OR 0 always gets x back. Is that making any sense? Let's look up the table, okay? Because the truth table is the most reliable source, of information. If you look at bitwise OR, we want the second one to be a 1, so we want to focus on these two columns. Oops, sorry, we want it to be 0. So this is the column that we want to focus on. This is also the other column that we want to focus on. if you look at this column, whatever x is, we get it back. Whatever x is here, we also get it back. Is that okay? So by making y 0, we always get x back after the bitwise OR operation. And that's why it's called an identity in mathematics. It's just like, in multiplication, multiply by 1 is the identity of multiplication. Adding 0 always gets you back the original thing, so 0 is the identity of addition in arithmetics. So for this reason, we also have an identity of false or 0 in bitwise OR. In bitwise AND, it is a 1, because anything AND 1 gets itself back. Anything AND 1 gets itself back. Okay. So that's exactly why, for all of the other bits that I don't want to touch, I make a 0. For the one bit that I want to turn into a 1, I specify a 1. So this way, I always make sure that the result has that bit being a 1, but without changing any of the other bits. What about turning something into a 0?
You get exclusive OR.
Not exclusive OR. Now, exclusive OR is good for one thing. It's good for flipping. If it was a 1, it turns into a 0. If it was a 0, it turns into a 1. But I don't want to check whether it was a 0 or a 1 before. I just want to perform one function or one operation, and want to make sure the result is always 0 for that bit position. And AND, exactly. So if I want to turn off a bit, okay, so in this case, oops, I think I got one too many zeros. We use a bitwise AND. So now the question is, what do I use with the bitwise AND so that it makes sure one particular bit ends up as a 0 but preserves all of the other bits? So I want to preserve this one. So all of these bits I want to preserve. But I have just demonstrated to you a little bit earlier what is the identity of conjunction. What is it? 1. So for all of the positions other than the one bit that I want to turn off, they are all 1s. For the one bit that I want to turn off, we put a 0 here. Because anything and 0 is always 0. 0 and 0 is 0. 1 and 0 is 0. So I'm guaranteed to turn off that bit regardless of what the original value is, without affecting the other bits. So this technique is called a bit masking, because I'm operating on one bit at a time without affecting the other bits. So are there any questions about these operations? No questions? Okay. Do you think this is only useful in embedded system programming or robotics programming? What about any other applications that might make use of this kind of technique working with the individual bits? Say again? Modeling? 3D modeling. How would you use a bitwise operation in 3D modeling? For color.
Like color mask.
A color mask.
Yeah.
Networking.
Well, networking will work. I'm not sure about 3D modeling. I'm not, well versed in that particular area, but I know in networking it does matter also. Okay, because when you specify a what we call a subnet mask, it is also it has to be seen in binary in order for you to determine what is the network address and what is the node address within the network. Okay, how many people are taking networking classes or have taken networking classes? No one. No one. Okay, that's all right. Okay. So these are the applications of bitwise operations. Now, when you use a bitwise exclusive OR, it is useful for toggling something. Okay, if it's on, you turn it off. If it's off, you turn it back on, which can be useful. For instance, if you have an LED and all you want to do is to blink it, to toggle it. So if it's on, it becomes off. If it was off, you want it to be turned on, then the exclusive OR operator would be useful. Very good. And there's one more application. One more application of bitwise operation is when you want to pack data as tightly as possible. Okay, what do I mean by that? Okay, let's think about a physical form that people have to fill in. Okay, on most physical forms, there are at least a few items where people have to circle like yes, no, okay, or just put a check mark, indicate yes or no, right? Okay, so for instance, give me an example of something like that.
Application, you know, where you
Yeah, go ahead.
Questionnaire, like a gender.
Well, gender is no longer, two choices these days. So I'm gonna stay out of that discussion. Well, something like if you're registering for a semester, in the form it might ask you, do you want to purchase a parking permit for this semester? Okay, so it's yes or no. Okay, true or false type of thing. Okay, how do we represent it in a computer? When you store it into a database or when you process it in RAM, how do we represent a field that is just yes, no, true, false?
They're probably in ones and zeros.
Everything is in ones and zeros. Very good. But in C and C++, okay, go ahead.
Oh,
Say again. Row sheet. Okay, thank you. See, row sheet is another good application, whether you're here or not. Yep.
Boolean exception.
Right.
The type way you store Boolean.
Right. If we had Booleans, that would be the type. But in C and C++ programming, we don't have Booleans. Okay, so the smallest type you can specify is a character, which is 8 bits.
So we can just make it a single bit on, so therefore if it's on, then the representation shows that.
Right, but the programming language itself does not support it. Okay, the C and C++ programming language as a whole gives you the smallest thing you can reserve and say this is a variable is a byte. Okay, is a character, a byte. Okay, so you're now allocating 8 bits when only 1 is required. It's kind of wasteful if you think about it. But most people don't think about it as wasteful because we have, computer memory in gigabytes and hard drive storage in terabytes or more. So most people think, it's okay, we are wasting 7 bits, it's no big deal. But what if you're programming for stuff that we were talking about earlier? You only have 32 bytes for everything that you want to store. Then it becomes kind of important, how you use your bits, right? So when you use 1 bit to indicate something that is only on or off, we get back to bitwise operations. So you're not going to waste an entire integer only to store something that is either on or off. You use 1 bit of a 16-bit or 32-bit integer to remember something that is either on or off. The other 31 bits can indicate 31 other things that are also on and off. Is that making any sense? Why bitwise operations may be useful for applications where you really want to shrink the amount of storage as much as you can. Okay. All right, so with this out of the way, we can now proceed with the next section. The next section talks about typecasting. Oh, integer types first, and then we'll go into typecasting. The integer type discussion is pretty much repeating stuff that we have talked about so far. I actually wrote this piece before getting back and write the other piece. So there's a lot of repeating information here. For instance, we have to represent everything as zeros and ones inside the computer. This is a 32-bit integer. Count the number of zeros and ones. There should be 32 of them. Nobody bothers, right? We talked about base conversion already. This is another way to do it, just using division and using remainder. But for base 2 conversion, it is actually easier. And we just think about terms in 1, 2, 4, 8, 16, and 32. Basically, it's the same thing as what we talked about and what we have done already in class, just presented a little bit differently. So I'm not going to go into here, and repeat the same information. There's no need to do it. So moving forward a little bit, base 2 to base 10, easier, because in the base 2 number, this tells you how many ones we have, how many 2s, how many 4s, how many 8s, and so on. So you just add up all those powers of 2 that are present, and you have the value. Okay. We talked about the width of an integer, w. The most negative value of a signed integer is 2 to the power of w minus 1, the negation of that. And then the most positive value is 2 to the power of w minus 1 in parentheses, and then the whole thing minus 1. So we talked about this already as well. So we can now start with pretty much in the middle of this document here and talk about C++ integers. Before we get into this, this is a lot of text. I don't want to really just read out, the text here. So instead, I will talk about a particular experience that my micromouse students at UC Davis had experienced. Okay? So every year, I will ask my students over there when I was teaching that class to write motion control software first, okay? Because it turns out to be one of the more complicated pieces. But I would ask them to write it on a regular PC and use a simulator to simulate the motor and make sure that everything is working before compiling the code onto the robot itself. Okay, because once it's on the robot, it's harder to debug. Okay, and they would do it. Okay, well, some teams will do it, and some teams will wait until like 2 months before the due date to do it. Not a good idea. So anyway, so some teams will develop the code on the regular PC using GCC, no problem. And then they would use a debugger or printf to help debug the software. And they will have everything debugged, proven to be working, but once they put it onto the controller, it doesn't work. Okay, it's exactly the same program, exactly the same compiler, and yet it does not work. Okay, the reason why it's not working is because int on the regular computer is 32-bit wide. But on a platform, on the robot platform, which uses an 8-bit processor, an int spelled exactly the same way only specifies 16-bit integers. So instead of 32-bit integers, now you have 16-bit integers. Well, okay, what is the big deal? I mean, it's safe space, right? Well, if you look at the range of values that can be represented, with 32-bit, you can represent approximately minus 2 billion to positive 2 billion. When you look at a 16-bit integer, it can only represent values from approximately 32,000 to positive 32,000. Quite a bit of a difference, right? And it turned out that the math that is involved in the calculation of motion control exceeds 32,000 by quite a bit. That's why the program worked okay when it was compiled in a 32-bit environment, and when it was compiled to a 16-bit environment, the same code doesn't work anymore. So the width of an integer is important. Now, there will be other classes where they can say, oh, that's easy to fix. You just have to say long int to make it a 32-bit integer. But even that is not a standard. Okay, there's no standard of saying what a long int is or what a long int is. Okay, you can keep piling up long and make it longer and longer. So that's why in this class, I want you to use these types instead. Now, in order to use these names, you have to include a special header file. I wouldn't call it special. It is always there. It's just that a lot of people do not know about it and not use it. But I want you to get you into a good habit of using standard int.h. STD is standard. So what it does is it defines some names for internal types. So after you include this header file, you no longer need to remember, oh, long int is guaranteed to be 32-bit, and then long int is guaranteed to be 64-bit. You just use these names to identify the width of the integer that you need. So int32_t identifies the integer type that, guess what, has 32-bit as a width. int16_t, 16-bit integer. int8_t, 8-bit integer. Okay. So in this class, I want you guys to use these particular types whenever possible. And as a programmer, you really need to know the range of the values of a particular variable or parameter. So you are the one who have to think about your program, the logic of your program, and say, in this particular case, I think this integer is well within the range of a 32-bit integer, or in this case, I think it might exceed the range of a 32-bit integer. Better use a 64-bit integer. But you'll be the one in charge, of determining what is the proper width of a particular variable. Yep. Floats are different. Okay, this is a little bit outside of this particular document. What he's talking about is a representation of non-integer values. It is called a float or floating point number representation. A float is always 32-bit, and a double is always 64-bit. That has to do with an IEEE standard for floating point number representation. So that's entirely separated from the interpretation of the word int, because float is guaranteed to use 32-bit and double is guaranteed to be 64. All right. Are there any questions about this particular example? So in this case, x can go from about negative 2 billion to positive 2 billion. Y can go from about negative 32,000 to positive 32,000. And z can go from exactly negative 128 to positive 127. Okay, here's a quick question. Okay, because we're talking about efficiency and stuff like that. So the question is, for efficiency, isn't it more efficient if we can fit something into an 8-bit integer? Is it always better to make it an 8-bit integer instead of 16 or 32? That's the question.
And you're saying relative to efficiency?
Right. Does it make your program go faster? Okay, go ahead.
I was going to say, it depends whether it's static or dynamic. Like, if it's a variable that updates something larger, you might want to allow for extra space.
Okay.
Or it's a crash.
So I was going to say, the overflow would probably add more time dealing with exceptions and things like that. And you'd have to handle that if you want to use a number in a very large.
So which one is more efficient? What does it make?
No, it's more inefficient to have to do other processes to handle this special situation than if you had a variable set aside and a larger.
Okay. Well, the answer to that question is it depends. But what it depends on is the architecture. In other words, if you have a 32-bit architecture like the Intel processor, or at least a 32-bit architecture, it means it can perform a 32 by 32 addition or subtraction in one single clock cycle. Making it a 16-bit or 8-bit operation does not speed it up. So there's no speed gain for this architecture when you use a smaller or a smaller integer. On the other hand, with the AVR architecture, the processor can only perform 8-bit operations. So to perform a 32-bit add, it has to combine 4 8-bit adds. So in that case, it does matter. Okay? So the answer is it depends on the architecture. And that's the end of the discussion of C++ integer types. I haven't really gone into unsigned integer types, and I will defer that discussion until much later, okay? Because it's not really, it's dangerous, okay? Getting into the interpretation of signed versus unsigned is a little bit dangerous, and I don't want you guys to have to worry about that stuff, at least for the time being, okay? So the next topic, and this class is going a little bit faster than the other class, so if you're getting stuck with a concept or something, you have to slow me down and let me know. So this slide, or this document, is about typecasting, coercion, and promotion. And all of these have nothing to do with people, okay? It has to do with types in C++ programming. All right. The rationale of these particular operations, and by the way, each and every single one of these is either an operator or it is an implicit operator. In other words, you can, in an expression, you can explicitly tell the C compiler and say, this was a smaller integer, now it is bigger. Or the other way around, okay? It was a 32-bit integer, now it is a 16-bit integer, Okay, so you can make it fit, a certain size. Typecasting refers to the operation that converts a value of one type to a value of a different type. That's basically what typecasting is about. And this is not the end of typecasting either. Okay, after this, we will not talk about typecasting for a little bit, but when we get to pointers, then we'll talk about typecasting again. In your other classes, in C++, in object-oriented programming, they will once again talk about typecasting, but in the context of classes and inheritance. Okay, so this is not the first time nor the last time we'll talk. Well, this is the first time, but not the last time that we'll talk about typecasting. But we'll only be talking about typecasting in the context of integer types for the time being. So in the current limited context, it means the conversion from one integer type to another integer type. And since they're all integers, all we are doing is to play with the width of the integers. Okay, is it 8-bit, 16-bit, or 32-bit? Are we promoting, making it wider, or are we, typecasting it to a smaller or narrower type of integer? That's the question. Coercion is a type of typecasting, and it is implicit. So when a typecast is implicit, done by the compiler, and you don't have to do a single thing, it is called coercion. So let's take a look at this integer, this example here. We have the usual main subroutine. That's the entry point of your entire program, and we have two integers. The first integer is called big int because it is a 32-bit integer, and the other one is called little int because it is an 8-bit integer. Okay. We assign a 0 to the little int, and then we say big integer is little int plus 1. Right there, without coercion, we have a problem. Because the addition operator preserves, there are two coercions on this line here. Well, okay, let me go back to the previous line. There's a coercion right there already. And you say, wow, what is the coercion? How can this already has a coercion? I mean, if you read the rest of the text, you will know. But if you don't, why is there a coercion already? Yep. Yep. Because if you just spell out a numerical value, it has an implicit type of just regular int. And on most platforms, a regular int is a 32-bit integer. So that means on the right-hand side, you have a 32-bit integer here, but we want to store it into an 8-bit integer on the left-hand side. So right there, the types are slightly different. C++ is a strongly typed language, which means when the type does not match, it's going to complain. But in this case, it's not going to complain because it knows how to do the conversion. So what it does is it will change the 32-bit representation into an 8-bit representation of 0. Okay. It does not take up any processing time. When this program runs, it does not really take up any additional time. But the compiler is internally doing the conversion in order to initialize little int. This one here has two coercions. The first coercion happens when we do the plus 1. Because once again, 1 is a 32-bit integer, little int is an 8-bit integer. So they are different. But with addition, it wants both sides to be exactly the same. So there's an implicit coercion here already to change little int to a 32-bit integer first, and then perform the addition. So the result of the addition, the sum, is already a 32-bit integer, and then that gets assigned to big int. So I correct myself. There's only one coercion, but the coercion does not happen with the assignment operator. It happens with the addition operator. And then the third line also has a coercion. In this case, we have a large integer on the right-hand side and a smaller integer on the left-hand side. So it has to truncate the most significant bytes to make it fit into the little integer. In other words, originally it has 32 bits. It has to basically chop off the most significant it has to chop off the most significant 24 bits in order to make it fit into the smaller integer. But here comes a question. What if big int is already greater than the range of little int? It won't complain a single thing. It will just do the truncation. It's just chopping up the bits and go, okay, now it fits. I don't care what it is or what it represents, and now it fits and I'm done. Which is not always a good idea. So are there any questions about coercion? It's just conversion that is built in that you don't have to explicitly state. So it's just an explanation of all of those here. Okay, let's talk about promotion. Sometimes coercion is not enough, and this happens when the intermediate result of a calculation may potentially exceed the width of the supplying variable and the storing variable. Okay, so let's take a look at this part here. Let's say that x is a 32-bit integer, y is also a 32-bit integer. Okay, so everything in this calculation are 32-bit integers. Let's take the multiplication into consideration first. This is multiplication, 32-bit on the left-hand side, 32-bit on the right-hand side. And multiplication preserves the width. In other words, you multiply a 32-bit number and with another 32-bit number. The product is automatically a 32-bit number as far as C++ is concerned. But that's not necessarily a good thing, right? Because if you just think in base 10, okay? And we are using, let's say, 2 digits in base 10. 99 is the largest number using 2 digits in base 10. 99 times 99, I don't need the exact answer, but how many digits do you need to store the product of 99 times 99? I don't need the exact answer either. Would it fit in 2 digits? No, that's it. Okay? So that means, when you multiply a 32-bit number to a 32-bit number, the product can potentially may require up to 64 bits to store. And yet, in this case, it's only using 32 bits. But then you might argue and say, oh, but since we have a division by y after this, it will come back and become a 32-bit number again. Well, but that's after you truncate the product to 32-bit from a 64-bit number. So the division comes too late. You have already lost the most significant 32-bit of the product by the time you get to the division. Am I making any sense? Okay. So that is why you want to do a promotion. In other words, you are manually, explicitly stating and say this x is use a 64-bit representation for this integer, for this x. And you only have to do it once. The reason why you only have to do it once is if you promote the left-hand side of a multiplication to 64-bit, the multiplication operator itself becomes a 64-bit multiplication operator. And once it gets to the right-hand side, it will say, oh, I can see that I am a 64-bit multiplication, but you're only giving me a 32-bit number. Let me promote that one automatically. So that's why only promoting one side will kind of fix the problem. But if you're in any doubt, it doesn't hurt to promote both sides manually. Okay. So that means the entire product is going to be a 64-bit number. As a 64-bit number, this is the dividend of a division. So this becomes a 64-bit division. As a 64-bit division operation, even though the program only specifies a 32-bit number as the divisor, it will automatically promote this 32-bit divisor to a 64-bit number before performing the 64-bit division. So everything that we do here, including the multiplication and the division, are actually in 64-bit, not 32-bit, even though the promotion is only to one of the expressions to the left-hand side of the multiplication. The automatic part is here. So there's a coercion. The coercion happens when we perform the assignment operation, because the entire right-hand side is now a 64-bit number. But the left-hand side x is still a 32-bit number. So when we perform the assignment, when we update variable x, it has an automatic coercion to change the 64-bit number to become 32-bit again. So this one is kind of complicated because some of it is explicit and many of these operations are kind of automatic. Are there any questions about this case? The rest of the text is explaining this, basically the same way as I did. Yep.
So when you're being explicit about what you want X to be, like you specify it to be a 64-bit integer, right? Do you need to put that at the beginning of the order of operations or at the leftmost side?
Can you ask that question again?
When you're specifying what variable you want or how wide you want variable,
Okay.
you need to do it at the beginning of the order of operations or for it to flow down to the rest of the calculation?
That's a good question. I would say at the beginning of the operation, because the compiler scans from left to right, so you still want to put that earlier. Or if you're in any doubt, you can always promote every single one, so that way you are sure that each one is treated as a 64-bit number before the operation. So are there any questions about promotion and coercion? They are basically both typecasting, except one is implicit, the compiler is doing it for you, and the other one is explicit. You are putting that into the code to make sure that the compiler perform that operation, to change the type, to change the width of the operand. Any questions about all this stuff? No. Okay. Yep, go ahead.
I don't know if this is a dumb question or not, but when you back up when we were talking about the integer types and how we need to specify whether it's like 32, 16, or 8-bit,
Right.
do you have an example of the best way to determine which one to use?
Sort of. I did not explicitly state that, but it is sort of in the answer, in the slide. The answer is sort of here. It has to do with this. It has to do with knowing, using this equation, you can figure out the range of values that you can represent using a particular width.
So basically, you would just need to think about what your program is doing then.
Yes.
And what
You
the
have to.
outcome would probably end up being. Okay.
Yeah. So you have to factor in how you use that variable in order to determine what is the correct range of values that it might represent.
Okay.
There are easy cases like that, like in a loop. If you use a variable to count how many times you're going through a loop, and you know ahead of time, the data size that you're dealing with, then you can just say, oh, since I know that there won't be any more than 1,000 samples coming in, and I just need to count up to 1,000, a short integer or 16-bit integer would do just fine. Or you can also limit using your application. You can basically, in the specification of the program, you can say this particular application can only perform arithmetic operations on numbers between this and that. So you can then use that as a limitation and say, okay, for anything else, it's outside of the specification of the program, so I don't have to worry about it. Any other questions? That's a good question. Sometimes it's harder to determine, especially when you're only writing a subroutine and somebody else is calling you,
That's true.
or you're calling another
So
subroutine.
you'd really need to know the scope of the entire program a lot of times, or if you write it one way, the other person, if they're calling your subroutine, would need to probably figure that out.
That is correct. That's why when you write your subroutine, it is important for you to specify the width of the parameters. So if the user, whoever is calling your subroutine, knowing is an int32 and still attempt to pass a value that cannot be represented as a 32-bit integer, the fault is not on your side. Because the person who's calling the subroutine should see that in the prototype of the subroutine and say, oh, okay, I cannot pass, let's say, a value of 6 billion to this subroutine because it cannot take it. All right. So any other questions before we end today's class? There's no homework due. Okay. The only work that you can do at this point because the homework is already due at this point. So the only thing you can do is to take the quiz, base conversion and bitwise operator exercise. Some people have taken it, and I looked at the grade distribution. I would say about 30% of the people who took the test probably can take it again, and just make sure that they get the concept down. And sometimes it takes a few times to get the concept down, thinking it in a different way. You can also look up Wikipedia, look up some other resources if my notes is not clear enough.
It's not timed or anything, is it?
It's not timed, there's no due date either, so you can do it all the way until the end of the semester. But I would do it as soon as possible just because the material is still fresh in your head.
So just to confirm, from your mail to say that if you go to grade and say no credits for the prerequisite, you might be dropped.
Yes.
I checked my grade and say no credit, but I do meet the requirement.
Okay, so let's see.